So thank you. So these are the last two lectures that I'm giving in this school. Since this is a school on strings, particle physics, and cosmology, in the last two lectures, I will try to describe some possible applications of the Swampland conjectures to cosmology and particle physics. So one of the interesting aspects about the Swampland is that many conjecture properties of quantum gravity are intricately related. And we have described some of these conjectures and their relations. And we'll continue on this quest in these two lectures today. Now, what is central to this web of conjectures is the weak gravity conjecture. I have presented a proof of the mild form of the weak gravity conjecture yesterday. And so since it is playing such a central role in the web of conjectures about quantum gravity, we'll start with a discussion of its applications to cosmology. Okay? So the weak gravity conjecture, if you recall, constrains the mass spectrum of particles that are charged under some gauge forces. Okay? Now, the Swampland distance conjecture that I introduced in the first lecture, on the other hand, constrains the field range within the validity of an effective field theory that couples consistently to gravity. Okay? So the question that you may ask is, what do they have to do with cosmology at all? As you will see, they can play an interesting role in constraining some models of inflation. Okay? Now, not all inflationary models would predict a detectable level of gravitational waves. Some of them do. As it will become clear later in the lecture today, we will refer to this class of models as large field inflation. Okay? So much of the efforts in the Swampland program has been in constraining models, certain models within this subclass of inflation. So not every models of inflations are severely constrained by the Swampland, but some of them do, especially those that give rise to interesting signatures, like detectable level of gravity waves imprinted on the cosmic microwave background. So in this lecture, in these two lectures, you will see three broad classes of applications of the Swampland. In this lecture, you will see how we can constrain certain models of large field inflation by the weak gravity conjecture and by the Swampland distance conjecture. And in the next lecture, we will discuss an interesting connection between the Swampland distance conjecture, how it constrains the field range of the validity of the EFT, with something called the de Sitter conjecture. Now, you'll see that this connection is only possible to be made at the weak coupling points. Nonetheless, these connections give us some idea, or at least give us a physical argument for why controlled de Sitter vacua are hard to come by. Okay? So we will see more explicitly in the next lecture. And finally, we will also see how some of the Swampland conjectures can say something interesting about particle physics, for instance, relating to neutrino mass and type with the observed cosmological constant. Okay? So this is the plan for the next two lectures. So let's first start with what the weak gravity conjecture can say about axions. Okay? So as you know, the idea of the axion was first introduced in the context of QCD to solve the strong CP problem. Okay? So the original idea is intimately tied to strong interactions. And in order for this hypothetical particle that we call axions to do its job, it has to enjoy a perturbative shift symmetry. Okay? So this is where you see the connections with the weak gravity conjecture come in. In string theory, we have many axion-like fields, and that is because in string theory there are many gauge fields. They are higher dimensions, they are not necessarily one-form gauge field, they are p-form gauge fields. But when you reduce these higher dimensional gauge fields to lower dimensions, this gauge fields becomes scalar fields, with the gauge symmetries becoming shift symmetry of the axions of the scalar fields. Okay? Now, for example, you can take a two-form field, like the two-form field that comes along with the metric, the NS, the Navier-Stokes B field. When you reduce it on a two-dimensional cycle in the internal space, this becomes scalars in 4 dimensions. And the original gauge symmetry of this two-form field becomes the shift symmetry of the axion. So the reason why I call this axion-like fields rather than axions is that most of them do not have anything to do with the QCD, with the strong interactions with QCD. So we will just broadly call this kind of fields with a perturbative shift symmetry as axion-like fields. Okay? So now the question is, what does the weak gravity conjecture have to say about axions? The conjecture, when it was first formulated, was about one-form gauge fields and how to bound the charge-to-mass ratio of particles in theories that coupled consistently with gravity. The connection is now clear because the axions or axion-like fields that come along in string theory have an origin as a higher-dimensional gauge field. So it's not unreasonable to try to find a duality frame where the axions turn into one-form fields. So even though, strictly speaking, we don't know how to formulate the weak gravity conjecture directly in the axion picture, we can do so in the dual picture where we have one form and charged particles. Okay? Now, the reason why it's subtle to formulate the weak gravity conjecture for axion is that the charged objects that we are interested in constraining are not particles, but rather they are instantons. And so the original argument of the weak gravity conjecture is about how black holes decay and the fact that there are infinitely many bound states. It's not clear how this argument can be made with instantons. Okay? Nonetheless, we can make use of duality to map some of these axions to the pictures where they become gauge fields and particles. And there we know how to formulate the weak gravity conjecture. And by way of duality, we can map these constraints in the U1 gauge fields particle pictures back to the axion picture, and then we find that the weak gravity conjecture takes this schematic form, which bounds the product of the axion decay constant or the axion field range with the instanton actions to be an order 1 number times m Planck. Now, to heuristically argue why this form of the conjecture why the weak gravity conjecture should take this form for axion, you can think of the instanton action as roughly the mass when you go through this duality map. And the inverse of the axion decay constant, which determine the coupling to the gauge fields and the matter fields, could be thought of as the charge. So this is roughly the charge to mass to charge ratio. So the weak gravity conjecture is a lower bound on the charge to mass ratio, and hence it turns into an upper bound on the product of the instanton action and the axion field range. Now this is very schematic. Let's go through an example more carefully to see how it goes. Let's be concrete and consider axions that come from, say, a two-form Ramon-Ramon field in type 2b string theory. You can get an axions by reducing this two-form on a two cycles. The instantons that couple to the axions are the D1 branes. They wrap around these two-dimensional cycles. The world lines are wrapped along the compact space, so that's why they are instantons. Now, if we start from this picture, it's hard to formulate the weak gravity conjecture, but you can take one of the non-compact directions, compactify on a circle, T-dualize, and decompactify. So this is a form of T-duality, but this is actually a T-duality done in the non-compact space. And so this has a name. It's called the Z-map. Under this Z-map, what you used to call an axion turned into a U1 vector field, a one-form field. It can be thought of as a three-form reduced on a two-cycle. And the instantons that we don't know how to formulate a weak gravity conjecture, can be turned into a particle. These particles can be thought of as D2 branes wrapping around the two cycles. So it still has a world line in the non-compact space. Okay? So now you can see that what we call instanton action and the inverse of the decay constants are now mapped to the mass and the charge of the particles in the type 2a picture under this Z-map, with some additional factors that are hard to guess unless you actually go through the duality map yourself. Now, here comes naively a problem, because when you go through this Z-map, when you decompactify the dimensions to get a non-compact four-dimensional space, the coupling constant blows up. Okay? So this G33 is the metric in the original frame. When you decompactify, that means that in the original frame, G33 shrinks to 0. So the coupling constant in the type 2a picture is infinite. But we do know how to handle this in string theory. The strong coupling limit of type 2a is M theory. So instead of formulating the weak gravity conjecture in type 2a, going through this Z-map, you can actually uplift everything to M theory and consider the charge consider particles in the M-theory pictures. These are M2 branes wrapping around 2 cycles. And you can work out what is the extremal conditions for black holes in this 5-dimensional gravitational theory, and use it to set as the lower bound on the weak gravity for the weak gravity conjecture. If you recall, the weak gravity conjecture says that there should be a state whose charge to mass ratio is bigger than 1. By 1, I mean the charge to mass ratio of an extremal black hole. So that 1 can be worked out if you work out the extremal conditions for a black hole in 5 dimensions. And there we find that this turned into a constraint on the charge to mass ratio of particles in the 5-dimensional theory, which in turn has an interpretation in terms of the instanton action and the decay constant. So now this is one of the examples, and you can go through other examples where the axion has a different life. It can come from different field. It doesn't have to be always Raman field. It could be Navier-Stokes B field or other fields. You can go through different types of duality, S duality, T duality, and in all cases, you can try to find a duality frame where the objects of interest are particles. And there you can impose the weak gravity conjecture. At the end of the day, what you find is something like this, that the bound of is a correlated constraints on the axion field range and the instanton actions up to 1 and order 1 factor times the Planck scale. This order 1 factor would be model dependent, depending on which axion you consider, but it's calculable. So in this example, it turned out to be square root of 2/3. In other examples, it's a different number, but it's all of order 1. Okay. Now, in fact, there's an easier way to see why something like this would follow if you were able to find a 1-dimensional circle to reduce. Right? So previously, I was being general. I was trying to do T-duality in a non-compact space. But suppose you have an internal 1-dimensional cycle when you can perform a reduction. Let's say you have an axion that comes from a U1 gauge field to begin, and for simplicity, we can consider a U1 gauge field in 5 dimensions, but it doesn't really matter. You can extrapolate what I'm going to say to other form of other dimensions and other P-form gauge fields. So consider U1 gauge fields in 5 dimensions. You can reduce it on the circle to get a 4-dimensional theory. And there you can see explicitly that the gauge field in 5 dimensions map into a gauge field in 4 dimensions plus a scalar field. And this is what we call the axion. And now you could work out the dimensional reduced action. The original gauge symmetry becomes the shift symmetry of the axion. So this is the 5th component of the gauge field. Now you could ask, what are the topologically non-trivial Euclidean configurations? These are the instantons configurations. They come from charged particles in the 5 dimensions whose world line are wrapped around the compact directions. So when the charged particles' world lines are wrapped around the compact space, they become instantons. So here you can now work out what is the instanton action. The instanton action should be determined by the mass of the particle, since it's the action of the world line of a particle. And it also depends on the size of the compact space. So that's why the instanton action is related to the mass and with the size of the compact space. Similarly, what you call the axion decay constant is determined by the coupling of the charged particles to the gauge field. Hence, there's the charge that appears here. When you make this identification and working out the weak gravity conjecture for the 5-dimensional theory, demanding that the charge to mass ratio is bigger than 1 in appropriate units, this turns into a constraint on the instanton actions and the field range. And as a result, you can argue that the weak gravity conjecture for axion takes this form. It's always an order 1 factor times the Planck scale. Depending on what theory you consider, this order 1 factor can vary, but you can work this out. Okay, so this is the story for axions. Now, because of this constraint, the weak gravity conjecture can say something interesting about inflation. And so we will first see how the weak gravity conjecture can constrain models of large field inflation before we turn to the Swampland distance conjecture. Okay? So inflation is arguably the leading paradigm for early universe cosmology. Okay? So other than solving the flatness and the horizon problem, it predicts generically a nearly scale invariant Gaussian curvature perturbations which is in very good agreement with data. The predictions that the spectrum is nearly scale invariant, namely it does not depends on the momentum scale or the distance scales, and that the correlation functions obey Gaussian statistics, seems to be in very good agreement with experimental data. And this curvature perturbations, which are due to quantum effects, sources anisotropies in the cosmic microwave background. So this is one way to test models of inflation. It also sources inhomogeneities in the large-scale structure. Okay? What is interesting is that different models of inflation would predict different patterns of anisotropies. So you can use experiments to constrain inflationary potential or models of inflation in general. Okay? Now, the taxonomy of inflation models has mostly been done through two of the observables. They are known as the spectral index, labeled as NS. This is a characterization of how the amplitude of the curvature perturbations depends on scale. If it is a completely scale invariant spectrum, the slope is flat, so the spectral index is 0. But in general, the spectrum can be tilted. It could be stronger at large scale or stronger at small scales, in which case this number is different with the convention, it's different from 1. Okay? So 1 is scale invariant according to a convention. Now, I have to explain a little bit what this tensor to scalar ratio means in order to draw the connections between inflation and the weak gravity conjecture. Okay? So this number that is denoted by R here is known as the tensor to scalar ratio. And this is because inflation predicts not only generically curvature perturbations that we have observed, but also gravitational waves. Okay? And the reason is any light scalar field, light means lighter than the Hubble scale during inflation, would experience quantum fluctuations. So, and the quantum fluctuations is stretched by inflationary expansions to cosmological scale. Okay? So imagine that not only the infraton field would fluctuate, but also the metric during inflation would also fluctuate since they are lighter than the Hubble scale. So what would happen is that they would get imprinted into cosmological observables. Now, although different models of inflation have very different predictions, they could give rise to various different shapes of the curvature perturbation spectrum, but we would expect generically there are two massless degrees of freedom, two like degrees of freedom that should exist at the time of inflation. Okay? So one is the Goldstone mode of broken time translational symmetry. This Goldstone mode is manifest as scalar perturbations. This is usually described by an inflaton field, but if you want to think of inflation more generally, you can just think of it as a Goldstone mode of broken time translational symmetry. And the amplitude of these scalar perturbations is set by the infraton speed. Okay? So if the field is not rolling at all, so then there's no broken time translational symmetry, but the rate at which it moves characterizes the broken time translational symmetry, and hence, no surprise, is the symmetry breaking scale that enters into the amplitude of the scalar perturbations. And this is just one of the scalar degrees of freedom. There's another like degrees of freedom that is guaranteed to exist because we have also perturbations of the metric. And so this is what we call gravitational waves. The fluctuations of the metric get stretched by inflationary perturbations. Eventually, they can be observed through the effects on the cosmic microwave background. And what is interesting is that unlike the scalar perturbations, which depends on several things, not only the scale of inflation, but also the symmetry breaking scale, the tensor perturbation spectrum depends only on one unknown, namely the scale of inflation, the Hubble scale, the only energy scale of interest. So that's why it's the holy grail in observational cosmology to observe these tensor perturbations, because before these measurements, we would have no independent way to see what is the energy scale that is involved. Okay? Now, to make the long story short, these two different types of perturbations can leave different imprints on the cosmic microwave background. And the way we could distinguish them is that the B-mode polarization, which is parity odd, can only be generated by the tensor mode and by the scalar mode. And if we were able to measure these tensor perturbations, it would be a telltale sign that there is some source of gravitational waves that are generated during inflation. The question is, what is the amplitude? If the Hubble scale of inflation is too small, this is unobservably small. And so even though, strictly speaking, inflation always predicts some level of gravitational waves, they may not be observationally relevant. Okay? So the connections with the weak gravity conjecture is through the following argument. Okay? Now, there are many models of inflation, and as I said before, not all models of inflation predict a detectable level of gravity waves. And then you can ask, what types of models would give you a measurable B-mode polarization in the CMB? So you can make a very simple argument. In fact, the argument was due to life many years ago. If you make some assumptions of what models of inflation you have, and these are not very crazy assumptions. So imagine that inflation, under the assumptions that inflation is realized by a single scalar field, effective scalar field, it doesn't have to be a fundamental scalar. And the scalar field has a flat enough potential that could realize slow rho, and the observed fluctuations are generated by the vacuum fluctuations of the infraton field, then you can show that the tensor to scalar ratio, which is defined as the ratio of the tensor spectrum with the scalar spectrum that has been observed since the Kobe experiment. This quantity is determined by one of the slow rho parameters that we call epsilon. It's a measure of the slope of the potential. Okay? Now, of course, if you have a more complicated model of inflation, when you have multiple scalar fields, this relation would not hold. But this is probably the most vanilla type of inflation model. Okay? So during the time when we observe the fluctuations, effectively, if the model of inflation can be described by a single scalar field, then this relation would still hold. Okay? And what does this relation tell us is that it ties the tensor to scalar ratio, which is an observable, to something which relates to the fundamental properties of inflation, namely the infraton field range. Okay? And this relation is sometimes known as the life bound, and I have sketched some of the steps here. The steps that went into it are not very deep. It just follows from some basic assumptions of slow rho inflation. Okay? But I want to draw your attention to the following few things. Strictly speaking, the life bound that you obtain under this assumption is an integrated relation. So it certainly ties the magnitude of the gravitational wave spectrum to the infraton field range, but it's not a point-by-point relation. Rather, it's an integrated effect. It tells us that during the course of inflation, when this number, the tensor to scalar ratio, can also change, you integrate over the course of inflation, that would give you the total field range that the infraton has traversed. But under the assumption that the potential is has the slow rho property, one can make some very reasonable approximation and relate it to one scale. Okay? And the argument is basically the following. So you can show that if the potential is realizing slow rho inflation, the tensor to scalar ratio does not change very much. You can actually calculate the rate of change of the tensor to scalar ratio with the e-fold of inflation. It goes as the small number epsilon. So it's not a very bad approximation to just take one scale, evaluate the tensor to scalar ratio, and multiply by the number of e-folds. And you need at least 50 to 60 e-folds of inflation to solve the flatness and the horizon problem. And when you put in the numbers, this turns into something of the order of 10 to the minus 3. If the tensor to scalar ratio that you measure is of the order of 10 to the minus 3, this would tell us that the infraton field range is bigger than or smaller than the Planck scale. Okay. Now, this is very interesting because there's an ongoing global experimental effort trying to detect gravitational waves implanted on the CMB. And the current bound on the tensor to scalar ratio, this number, R over here, is about 0.064 at 95% confidence level, combining results from many different experiments, Planck, BICEP, and baryon acoustic oscillations. When you combine these different experimental bound, you get a number that is still within the ballpark of the life bound. It's 0.06 roughly, and it's still not far from the target value of 10 to the minus 2 or 10 to the minus 3. And besides, there are many different experiments trying to target observations of B modes at the sensitivity of 10 to the minus 2, and perhaps even more ambitiously at the level of 10 to the minus 3. So it's not unlikely that within a reasonable time scale, we will be able to close the gap on whether inflation is realized as large field or small field. If you don't find anything by the time we reach the 10 to the minus 3 level, it's very likely that models of inflation which has transpunction field range are excluded. But when you find something, a potential signal, that would be extremely exciting. Okay? So that's one of the reasons why there have been a lot of activities trying to see whether you can get large field inflation in a consistent theory of inflation coupled to gravity. Okay? So let me just summarize some of the statements one could potentially make if there's an observation and why this is interesting. So as we have seen, the so-called life-bound tied the tensor to scalar ratio with the infraton field range. And so if you were able to measure B mode at the level of 10 to the minus 2 or 10 to the minus 3, this would tell us whether inflation was large field or not. Okay? So this is one point. And another point is, as I emphasized earlier, the scale of inflation is tied to the amplitude of gravitational wave. So that means that the tensor to scalar ratio depends on the scale of inflation. Okay? And you can translate the scale of inflation in terms of the tensor to scalar ratio. If you measure the tensor mode at the level 10 to the minus 2 or 10 to the minus 3, this would tell us that the energy scale of inflation is order of the Gutt scale, a few orders below the Planck scale. And since this scale is not far from the string scale or the Planck scale, it's not unexpected that maybe some stringy physics would come into play. Okay? It's precisely because of these two points over here that large field inflation is sensitive to UV physics that generate a lot of activities in trying to connect quantum gravity with inflation. Now, the reason why the second point, the life bound, is important is that the infraton potential is subject to all kinds of quantum corrections. So given that you have a nice inflationary theory, you could ask whether the potential get corrected when the infraton field traverses over a very long field range. Normally, higher dimension, these are the irrelevant operators that correct the infraton potentials. Usually, irrelevant operators are not very important. However, if the field range is super Planckian, when the change in phi is bigger than all possible cutoff scale that you could imagine, then these higher order corrections can significantly correct the infraton potential. The degrees of freedom can change. What you consider as light degrees of freedom can become heavy degrees of freedom and vice versa. And so you don't have complete control of the inflationary theory unless you know how these corrections look like. Either you have a way to compute these corrections explicitly, or you have a way to argue why these corrections are small. Okay? Now, since there are infinite number of potential corrections, these are infinitely many higher dimension operators, trying to control these corrections one by one is rather hopeless. Okay? So a more promising approach is to come up with a symmetry that forbids or controls these higher order corrections. Okay? So this is the connection with the earlier discussions about axions. So earlier we said the weak gravity conjecture constrains the axion field range in terms of the instanton action. Okay? So now we can see how the weak gravity conjecture can constrain models of inflation that involve an axions. So as we argue, trying to control these corrections one by one is not very promising. And that explains why a lot of models of large field inflation involve one way or the other an axion field. Okay? So axion fields, by definitions, enjoy a perturbative shift symmetry. So at the classical level and at the perturbative level, there are no potentials. So then the potential is obviously flat. And it could receive corrections from non-perturbative effects. Instanton effects can generate a potential for the axion field. And so the resulting axion potential is periodic, with the periodicity set by the so-called axion decay constant or the axion field range. And so the question is, how far can we go in the axion field space if we want to traverse a super-Planckian field range in order to generate large enough gravitational wave, this axion decay constant ought to be bigger than the Planck scale. Okay? Now, I would, to be clear, I would call this type of axions periodic axions. This is to be distinguished from the monotony axions that I would talk about later on. Periodic axions are axions that have a compact field space. Here, the field space is limited to be within this range from here to 2 pi of the fundamental domain is defined by the decay constant. Now, you can see how the Requiere conjecture can constrain model of this type. Okay. Now, we see that to get slow roll, in fact, for this model, in order to get slow roll, the decay constant has to be super-Planckian. If the field range is not long enough, the potential is not flat. This is not even to talk about getting a super-Planckian field range. Of course, it turns out that in order to get a flat enough potential, you also generate a significant level of gravitational wave. The usual way to realize large field inflation is to imagine that this is an axion potential. It has a usual cosine form with the scale of the potential that is instanton suppressed. And so imagine that you have an instanton action that is S instanton. The leading instanton effect is suppressed by e to the minus s. And even though in general there could be higher instanton corrections, they are even more suppressed. They are more exponentially suppressed. So models of inflation of this type have been proposed. They go under the name of natural inflation. Natural because axions are pseudo-Goldstone bosons. Okay? And we see that the Requiere conjecture says that this type of models are in tension with quantum gravity constraints. And the reason is the Requiere conjecture is a bound on the product of the decay constant and the instanton action. For the model to generate a detectable level of gravitational wave, the field range is bigger than the Planck scale. And that means the instanton action has to be small in Planck units. So this assumption that is oftentimes made about the higher order corrections being unimportant cannot be made anymore. The higher instanton effects are not as suppressed as you want. The instanton action is much smaller than the natural units, Planck scale. And so you would have to sum over all these high instanton effects. Now, whether you know how to sum over the instanton effects or not, it would significantly change the properties of the potential. In particular, the field range will no longer be set by the first harmonics. When you have all these higher harmonics that come into play, the field range could be significantly reduced. So this tells us that simple models of axion inflation are in tension with the weak gravity conjecture. Now, this is also consistent with what we know by systematic searches for super-Planckian decay constant in the landscape. So about 10, 15 years ago, actually 15 years ago, a rather systematic study surveying different formulations of string theory had concluded that axions with super-Planckian decay constants do not seem to arise in control limits of the theory. So it's not that you cannot find models of string compactification where the decay constant is super-Planckian. You do find examples of that sort. But precisely when the axion decay constant can be made large, you find that higher order instanton effects are important, which you cannot ignore, or you are forced to go to a region of the moduli space where some additional states become light. Okay? So now the question is, we have seen that the axion field range for an individual axion is bounded by the weak gravity conjecture. Could models with multiple axions solve the problem? Okay? So if one axion has a limited field range, can the presence of multiple axions, which, as I mentioned, is very generic in a string compactification, can multiple axions save the day? It turns out, at least in the simple versions of the models that have been postulated, this could not help. You can, in principle, extend the effective field range of the axions if you have multiple axion fields, but the simple models that have been proposed do not satisfy the so-called convex Hull condition, which, as I reviewed in the first lecture, is the multiple field generalizations of the weak gravity conjecture. Okay? So let me just recall for you what the convex Hull condition is. So the weak gravity conjecture demands that an extremal black hole can decay. So for a single U1 case, it amounts to finding particles with charge to mass ratio bigger than 1. If you have multiple U1 field, the requirement is for all the black holes that lie within this extremal ball to have a channel to decay. And this turns into a condition on the convex Hull generated by the charge to mass vectors. So in theories with multiple U1s, you ought to find states with a charge to mass ratio that is big enough to generate a big enough polygon that contains this extremal ball. Okay? And this was a statement about U1 gauge fields, but since we already gone through the duality map in the beginning of the lecture, you could extrapolate these statements to inflation as well. So the statement would be that the charge to mass ratio vectors generated by the instantons should be big enough to contain the extremal ball where the extremal black hole lies. And so all these black holes would have a channel to decay. Okay? So what are the models of inflation with multiple axion fields that have been proposed, trying to get effective super Planckian field range? So one of the ideas is known as axion alignment. Okay? And the idea is the following. So if you have multiple axion fields, each of these axion fields will have its own periodicity. So non-perturbative effects could be generated. So they both, in general, the two axion fields would, in general, pick up a potential, pick up a mass from the non-perturbative instanton effects. So both of them would be massive. However, if the instanton effects are tuned in such a way that there is only one linear combination of the axion that pick up a mass, the orthogonal direction would remain a flat direction. So it's not very generic situations. You can imagine tuning your model parameters to achieve this. And this amounts to tuning the axion decay constant of the individual axions. So if you were able to tune the decay constant in such a way that only one linear combination of the axions pick up a non-perturbative mass, you have a flat directions. You can go as far as you like in that direction. Okay? Now, this is not what we want. You can perturb the relation a little bit, and it's not difficult to convince yourself that by doing so, you could generate a direction that is long enough to be bigger than the Planck scale. So that's the idea of axion alignment. Alignment in the sense of tuning the decay constant of the individual axions. And you can see that this model cannot be made compatible with the weak gravity conjecture because the aligned axions generate a convex Hull, which is very thin. It does not contain the extremal ball. So there are still some black holes that don't find a decay channel. This is one idea. And another idea is known as inflation. Okay. So imagine that you have more than one axion field, and you can inflate along an arbitrary direction in the multidimensional field space. And if you inflate along some diagonal directions, this would buy you a factor of square root of n, where n is the dimension of the field space. And so naively, it appears that you could gain an effective field range. If each individual axion has a field range of has a subplanckian field range, this root n factor could enhance the effective field range. If you have thousands of axion field, this could gain you a huge factor that makes the effective field range super Planckian. However, as you can see from the picture here, this does not help either, because in the high dimensional field space, the charge vectors representing the instantons have to be enlarged. They have to be longer than just one. They have to be enlarged by a factor of root n in order to contain the convex Hull. So thereby undoing the root n factor that you gain by inflation. Okay? So in both cases, you find that the models are not compatible with the weak gravity conjecture. Now, as with any no-go theorems, there are always some loopholes. So a simple loophole you could imagine is that suppose in addition to the axions, in addition to the instantons that generate for you the axion potentials, there are some other instantons, which you can call the spectator instantons. They are denoted by these contributions over here. And if you have an instanton that have a very large instanton action, so it does not contribute much to the potential. You can basically ignore its contribution at all. But if the corresponding axion decay constant is very small, it could still satisfy the weak gravity conjecture. So the whole purpose of this spectator instanton is to satisfy the weak gravity conjecture. It serves no purpose at all. It gives a very small contributions to the potential. But in the presence of this additional instantons, it could generate a big enough convex hull to contain the extremal ball, and could be made compatible with the weak gravity conjecture. That means that if you allow a small perturbations to your potential, something that give a negligible contributions, but nonetheless satisfy the weak gravity constraints, you have a model of axion inflation with super Planckian field range. Pictorially, you can think of this big overlapping potential as the one that generates predominantly the potential for you. It has a super Planckian field range, and on top of it, there are some small perturbations due to the spectator. The spectator gives a negligible contribution to the potential, so there are only small wiggles. And the fact that these small wiggles have a very narrow field range satisfy the weak gravity conjecture for you. And what is interesting is that these tiny wiggles in the potential could lead to some interesting signature as well. And for other reasons, wiggly potentials have been considered in the inflationary context, and they were shown to give rise to interesting signatures, such as non-Gaussianities. So it's not completely, so first you could save some of this axion inflation model by introducing the spectator. And secondly, it comes with signatures, interesting signatures on its own. Now, this was the mild form of the weak gravity conjecture that I mentioned, right? Because the weak gravity conjecture has several forms. The mild form of the weak gravity conjecture only requires some states to satisfy the inequality. And we use this spectator instanton to satisfy the inequality. But I also mentioned in the last lecture that there are stronger versions of the weak gravity conjecture that requires infinitely many charge states in the U1 particle picture. In particular, the so-called sublattice weak gravity conjecture requires that there is a finite sublattice of a full charge lattice. At every point in the charge lattice, there is a super extremal state. Okay? So even stronger versions of the weak gravity conjecture, like the sublattice weak gravity conjecture, can be evaded with this spectator instantons. So imagine you fill all this sublattice with an instanton that barely saturates the bound. Out of this sublattice of instanton, you have two of such instantons that are particularly dominant in the potential. It has a very small instanton action. So by construction, this model satisfies the sublattice weak gravity conjecture. Every sublattice points of the charge lattice has a super extremal state, except that two of such points are extremely super extremal. And so with this spectator instantons, you can also satisfy the stronger versions of the weak gravity conjecture. Okay? Now, this may sound very contrived to you, and I agree. And the reason why I bring up this loophole is not because I find this particularly pleasing or particularly natural. The main message I want to make here is that this loopholes, it's not that these loopholes are very natural or can be realized very easily, but you get the message that models satisfying the weak gravity conjecture always come with some extra baggage that do not seem to be necessary from a pure low energy point of view. So it's really from the constraints, the Swampland constraints, that we need to add in these extra ingredients. And sometimes these extra ingredients that you add in may come with interesting signatures as well. Okay, so how am I doing with time? I have about... Okay, good. So, so are there any questions at this point before I move on to a slightly different topic? Yes?
I have general questions about large field inflations. I mean, apart from specific axiom models. Since the fields are large, wouldn't it be severely limited by your Swampland distance conjecture?
Very good. I'll come to that later on. I am trying to restrict different types of models. So these types of models are more naturally constrained by the weak gravity conjecture. And this is actually the next topic I'm going to discuss. This, in the case of axial monodromy inflation, there's no clear way of using the weak-gravity conjecture to constrain it, but we can use the Swampland distance conjecture to constrain it. So any other questions before I move on to this slightly different class of models? Okay, now the axions that I consider up to this point are what I call periodic axions. It has a compact field space. An interesting idea is axial monodromy inflation. So unlike the periodic axions that we discussed before, the monodromy axions are axions with a non-compact field space. Okay, so so this non-periodic axions has a broken shift symmetry before the non-perturbative effects set in. And so you can think of these axions as having a quasi-periodicity, but it goes on, and in general, it could have a non-compact field. You open up the axion field space by breaking the shift symmetry through perturbative effects. And now the reason why I considered earlier periodic axion is that monodromy axions are different types of axions. Since it already has a mass before non-perturbative effects kicks in through the map of dualities that I mentioned in the beginning, they are mapped to some massive U1 gauge fields. And so the weak gravity conjecture is about long-range force. And so this massive U1 gauge fields do not lead to long-range force, so we cannot immediately apply the weak gravity conjecture to this class of models. So that's why I delayed the discussion until now to see how other Swampland conjectures can constrain models of this type. Okay. So as you correctly pointed out, the Swampland distance conjecture is a much more general statement about field range. Can the Swampland distance conjecture exclude models of axial monodromy inflation? Okay. So we'll have to go a little bit into the details of these models before we can see how the Swampland distance conjecture can constrain them. Okay. So when the axial monodromy idea was first proposed, the shift symmetry was assumed to be broken by the coupling of the axions to branes. Okay. And so the models are somewhat difficult to construct. Explicit constructions involve ingredients that are hard to describe, maybe hard to realize. For instance, one of the explicit models that were proposed back then involve some NS5 branes and some anti-NS5 branes wrapping around homologous cycles in different warp throats. Okay? And so the NS branes wrapping around some cycles, some 2 cycles, give rise to the coupling of the axions to these wrapped branes give rise to a potential for the axion, so that's why you could pick up a potential. And the reason why you have NS5 branes and anti-NS5 branes is to satisfy the Gauss law constraints. They are charged objects, so you ought to have branes with different charges in order to satisfy the Gauss law conditions. And now, as you can see, the model is slightly difficult to implement, and so it will be harder to quantify the corrections to the effective field theory if you traverse a super Planckian field range in these models. Okay? So turns out the idea of axial monodromy can be made more general. Okay? So the whole idea is to be able to give a mass to the axions before the non-perturbative effects set in. So an idea to make simpler models of axial monodromy model is known as FluxMonitorMe or F-term axial monodromy inflation. And the idea is that in the same way that moduli are stabilized by fluxes, as in Giddings, Katru-Polchinski type constructions, you can use the same idea to generate the potential for the axion. And so here I could sketch a simple model for you to realize this idea. So let's say you take the kinetic term for the Ramon-Ramon forms in 10 dimensions to begin with. So G here is the sum of the Ramon-Ramon forms. So it contains F here is the field strength for the Ramon-Ramon P minus 1 form. This is the NS2 form field and the corresponding field strength. curly F here is a formal sum of all the Ramon forms. So this is the kinetic terms for the form fields in 10 dimensions. And the point is, this gauge fields, this higher dimensional gauge field, when you reduce it on the internal space, they would give rise to axions in 4 dimensions. So just from the kinetic term, it would generate a potential in the resulting 4-dimensional theory because the gauge field appears explicitly in the kinetic term. When you reduce these actions to 4 dimensions, it would give rise to a potential for this whole bunch of axions. Okay. So if you were to carry out this reduction, you'll find that the corresponding 4-dimensional actions can take this form. This is the part that involves the axions. Okay? So it can be written in this form where the axion is coupled to some 4-form flux in 4 dimensions. So I have to explain a little bit this notation here. This is the potential that you get from reducing the kinetic term. And F4 is some 4-form flux in 4 dimensions. Theta is your axions. And this is the kinetic term for the 4-form flux. It depends on, in general, also on the saxion partner of the axion. Okay? So the saxion is the scalar that comes along with the axions. It cannot depend on the axion because of the shift symmetry. So this is the general form of the 4-dimensional potentials that you get by reducing this flux-induced kinetic terms. And so this is the place where the axions appear. And this term that I call rho depends on the axion as well as the quantized internal fluxes that you switch on. And this functions that multiply the kinetic term for the 4-form flux depends on the saxions in general, and it cannot depend on the axion because of the shift symmetry. Okay? So all the axion dependence are here, and all the saxion dependence are here. Okay? Now, this three-form flux, this three-form field corresponding to the 4-form is not dynamic, so you can integrate this out, and there you get the scalar potentials for the axions. And notice the interesting structure of this potential. It's a function of the axion field. The axion and the saxion dependence are nicely separated out. So there's a piece overall that depends on the saxion partner of the axions, and this is a function of the axion. So this would give you a potential for the axion field. Okay? So this looks a bit abstract, so we could take a particularly simple example where there's only a single 4-form and a single axion that couple to it. And so the model could be greatly simplified. So you can imagine this model as coming from some flux compactification in string theory, and when you reduce it on the internal space, they would give rise to a 4-dimensional action of this type. And the point is how this model could have control corrections. Okay? So this is the structure of the potential. And what I call F here depends on the saxions. And carrying out the procedure that I outlined before, you can integrate out this 3-form gauge field. And as a result, you generate a potential for the axions. And the quantity here, which defines the function rho, depends on the quantized fluxes. So in this model, the quantized fluxes are labeled by F0 and M. So they take integer values. And so this gives us a potential of this type. And if you just look at the structure of the potential, it looks like one of these chaotic inflation models, where the potential takes a quadratic form. Okay? But there are some slight interesting differences. One of them is that this potential tell us that there are several branches. And there are several branches labeled by the value of the quantized fluxes. And this potential tells us that the shift symmetry is broken. So that's why the axion take up a perturbative mass. There's a mass term for it. And when you shift the axion field by a constant, it's no longer a symmetry of the theory. However, there's still a remnant. There's a combined discrete symmetry, which corresponds to shifting the axions accompanied by a shift of the flux. Okay? So pictorially, you can see this potential in the following form. There are multiple branches. labeled by the value of the quantized flux. And the periodicity is broken. If you look at only a single branch, it's not periodic in field space. But the periodicity is restored if you consider the collections of all these branches of the potential. This multiple branch potential restore the periodicity. And so the reason why the higher order corrections are under better control is because there's an underlying symmetry. Here you see that there's a shift symmetries that combine the shift of an axion with the shift of the quantized flux. This shift symmetries forbid corrections that are not respecting that symmetries. And you can convince yourself that the corrections of the potential is not arbitrary in terms of powers of the field axion. Rather, it has to collect into corrections of the type of that looks like powers of the potential of the flux or power of the potential itself. Okay? So in this example, where there's only a single axion and a single four-form flux, you can even relate these higher order corrections, which package themselves into powers of the four-form flux in terms of powers of the potentials that you begin with. And since your potential has to be Subplanckian to begin, and these higher order corrections are under better control. If it was not because of the symmetry of this combined shift symmetry, you would have other corrections that don't look like powers of the four-form flux, but rather powers of the potential, and those potential corrections are not under control if you traverse over super Planckian distances. Okay? Yeah.
I guess you don't mean that you can directly jump from one property to another.
That's right. So there would be a non-perturbative transition when you go from one branch to the other, and you can estimate how big is the transition rate. And turn out it's not very. It's not happening at a very high rate, so you can consider. That's right. That's right. So as far as the infraton is concerned, it doesn't see a periodic potential, but the underlying structure, if you include all these branches that you can, in principle, tunnel to, restore the symmetry. Okay. Very good question. All right. Now, this may seem a bit mysterious, how I write things in terms of this non-dynamical four-form and integrate things out. If you find that this apparent loss of symmetries and the restoration of the symmetries by taking into multiple branches kind of mysterious, you can rewrite this in a form that may make you happier. So instead of describing the axion in terms of a pseudo-scalar, you can write it in terms of its dual two-form. And what this axion four-form coupling that I described in the previous slides can be expressed in terms of a Stuckelberg coupling. Okay? So in terms of the two-form, this two-form is eaten by a three-form vector field, just like how the Stuckelberg mechanism works for one-form and scalars. And so this is the dual way of explaining why the axion pick up a mass. Through the Stuckelberg mechanism, the two-form is eaten by the vector field and hence gain a mass. And the model has a manifest gauge symmetry, which corresponds to the shift of the three-form and the shift of the two-form. And this is the underlying gauge symmetry that protects the axions from dangerous UV corrections. Okay? So either way, whether you want to write it in terms of the axion four-form coupling or in terms of this perhaps more clear picture of two-form and three-form interacting through the Stuckelberg couplings, it shows that the model is under better control, subject to quantum corrections. Okay, now this is a particularly simple model, and if you were to embed this into string compactifications, you don't always have such a minimal ingredients. You would have a lot more fluxes, and you would have a lot more axions. Okay, so how do we deal with situations like that? So there will be some changes in the model that makes it slightly different from what we explained before. And in particular, the function that I call rho is the shift invariant function. Remember, this function is the combinations of the flux and the axions. This is a particularly simple example. In general, if you have multiple axions, multiple fluxes, this shift invariant functions can include multiple axion fields in it. They could all shift together in a collective way. And so this shift invariant functions can involve mixing and higher order terms, and that would give rise to a potential that's more general than the chaotic inflation model that I described. So this means that the type of potentials that you can consider within this framework is much richer. Another thing that would change is that when you have multiple free forms, it's true that gauge symmetries restrict the form of the corrections to be powers of the four-form flux. But it's not necessarily possible to rewrite these corrections in terms of powers of the potential. In the case of a single four-form, there's no other choice. You can always swap one with the other. But in general, if you have multiple four-form fields, the corrections are not simply powers of the potential, but rather powers of this shift invariant functions. Nonetheless, if you can show that this shift invariant function is Subplanckian, again, the corrections are under control. They are not arbitrary. You cannot write down arbitrary powers of the axion fields because they don't respect the symmetry. So compare with general models of large field inflation, these models are slightly under better control. Another point that would become useful later on to answer Suk's questions, how the Swampland distance conjecture can constrain models of this type. We should note that the structure of the potential has this form. There is an axion field, and the potential coupled the axions with the saxions. So as the axion move over a super-Planckian distance, there would be a corresponding back reactions of the saxion field. If you were to minimize the potential, if you go to a different point in the axion directions, the corresponding saxion field would also shift. And so this would have an interesting implication on the Swampland distance conjecture that we are going to turn to. Okay? In fact, just two points to summarize before we go to the Swampland distance conjecture. And the first is that, at least in the models that I have described, axion monodromy model comes with a symmetry-based protection mechanism. So it is not that we could forbid all corrections to the potential, but symmetry restricts the type of potential to a certain form. It's under better control, and the corrections should always go like the shift invariant functions rather than the axions themselves. And as you also mentioned before, there are transitions that could take you from one branch to the other. The transition rate you can compute, and we find that the transition rate is not very fast, and so you can, so it doesn't forbid the axion fields to be displaced very large distance away from the origin, so you could have super-Planckian distance. Nonetheless, it cannot go parametrically large. As you move the field further away from the minimum, the transition rate will become big enough that it's favorable for the field to tunnel to a different branch. Okay? But for the purpose of inflation, you only need to go super-Planckian by a factor of 10 or so, and it's achievable in this class of models. Okay, now that's the point where we could bring in the Swampland distance conjecture. The models can evade the weak gravity conjecture simply because they are not corresponding to long-range force when you map the massive axions to a vector field. But the Swampland distance conjecture is a more general statement about field ranges. Could it also limit the field range of axion monodromy inflation? Okay. Naively, it doesn't seem to be the case because if you recall, the argument that I gave earlier were made for simple examples like Kaluza-Klein reduction on the circle, where you see that the field that is being considered appears in the kinetic term of its own. Okay? So this is the reason why going to large radius or small radius would bring in exponentially like states. Exponential because this is not the canonical kinetic term. In terms of the canonical field, the Kaluza-Klein states, which goes inversely with the radius, would become exponentially like in the proper coordinates. So this is not the case for the axions because axions have a shift symmetry. So unlike the radion, its kinetic term does not depend on its own, on the field of its own. In particular, you can write down the kinetic term for the axion field for the axial dilaton as an example. So this is the complex field. The imaginary part is the axion field, the corresponding scalar, the real part of this chiral multiplet is the saxions, and the kinetic term, the Kähler potential is given by log of the real part of this chiral field, and the kinetic term for the saxions depend on the saxion, but the kinetic term for the axion cannot depend on the axion because of the shift symmetry. In fact, it only depends on the saxions. Okay. But this is where the point that I made earlier would come in handy. We said earlier that the potential takes this form, and even though the kinetic term for the axion has no axion dependence, but implicitly, because the potential mixes the two, if the axion field moves over a super-Planckian distance, you ought to change the corresponding saxion field. So there's some implicit dependence on the saxion field on the axion. And so you could ask, what would be the corresponding field range that the axion can traverse, given this back reaction effect? So the question is, how do we estimate this back reaction? One way to do that is to consider the trajectory traced by the minimum of the potential as we vary the axion field. So without going into specific details, you could already imagine that to lowest order, the saxion field would be displaced by something that is at least linear with the field. Right? This is the lowest order approximation. There could be higher order effects, but suppose you displace the field slightly from the axion field slightly, the corresponding shift of the saxion would be linearly, at least linearly going with the axions. So that means that the kinetic term would now dependent on the axion field. If you go to large enough field distances, this will be the dominant effect. And so indeed, you find that the axion field range also goes as a log, as the Swampland distance conjecture suggests. Okay? So the question is, what is this critical field range? So I labeled this critical field range by lambda, by a number, and this set the scale at which the exponential growth of the like states would set in. And this number is of order 1 if the axion and the saxion have about the same mass. But if they have a significant hierarchy in terms of the masses, this number could be significantly enhanced. And intuitively, you can understand how big is the back reaction of the saxion depends on how heavy it is compared with the axion field. And if there's a hierarchy in terms of the masses, it would delay the onset of this log behavior of the field range. Okay? So the point is, it can be enhanced if there's a mass hierarchy. And if, for the purpose of inflation, you only need the field range to go slightly above Planckian values. So a factor of 10 would be sufficient to give you a detectable level of gravitational wave. So could it be that the field range can be enhanced by precisely this mass hierarchy? Okay. In fact, as a comment, we would expect, not only because this hierarchy is necessary for generating a significant gravitational wave for these models, we actually need to maintain this hierarchy in order to work within the framework of single field inflation. Right? So the assumptions that went into the life bound that I described is that the inflationary model is described effectively by single degrees of freedom. And that is because the other fields are heavier enough that we can integrate them out. And if they are of the same mass, then we could not really integrate out the saxion field. We would have to work with at least the two-field models. So in any case, we need to maintain a hierarchy between the axion and the saxion to be consistent with the single field framework. So the questions that one would ask is this way of estimating the estimating the field range the correct one when in general there is no mass hierarchy? And secondly, when the mass hierarchy is weak, or when there's no mass hierarchy, is the field range limited to be of order 1 times m Planck? Okay? So if you look into a little bit more in details, you find that the answer is no to these questions. And the reason is, when we estimate the field range by tracing the minimum of the potential as a function of the saxions, we are ignoring the kinetic term. We are only looking at the minimum of the potential. But the kinetic terms in general cannot be ignored. And if we were to assume that the kinetic terms can be ignored, this implies by default that the trajectory is a geodesic in field space. And it is very well known that in the context of inflation, that when you have theories with multiple fields, the trajectory is not, in general, a geodesic. Okay? And if you were to just minimize the potential with respect to the field and substitute it into the, if you were to just minimize the potential for every single value of the light field for the heavy field, it wouldn't solve, in general, the equation of motion. Okay? So again, given the time constraint, maybe I would just tell you that if you were to solve the problem numerically, you'll find that if there's no mass hierarchy, the dynamical field range can be much bigger than what you have expected by just minimizing the potential, simply because the kinetic term for the heavy fields cannot be ignored. And if there's a significant mass hierarchy on the other hand, we already seen that the critical field range is enhanced by the hierarchy. So if the whole point of the discussion is whether you can go to, say, 10 times or 15 times the Planck scale, a priori, the Swampland distance conjecture cannot rule out models of that type, although it would be challenging to actually construct an explicit model that gives you, say, 10 times the Planck scale traverse to get a model with field range that is of the order of 10 times the Planck scale. But in principle, it is possible. Okay? So let me just briefly wrap up. And so the upshot is that the weak gravity conjecture and the Swampland distance conjecture alone do not exclude axial monotony inflation model. Now, I'm not saying that these models are completely airtight. It's possible that there are other quantum gravity considerations that we could not imagine at the moment. And maybe when we look at it more closely, they are excluded one way or the other. But before we know what they are, we should keep an open mind. And I should also like to point out that there has been some interesting work recently in providing further evidence for the Swampland distance conjecture by studying the complex structure moduli space of type 2 B compactifications. And so by going to infinite, so you could go to infinite distance in field space if you approach a singularity. And what one finds is that indeed there is a tower of massless states that arise at the singularities. These massless states are the BPS states that corresponds to wrapped D3 branes. So this would be an example where the Swampland distance conjecture and the asymptotic limit at large distances can be confirmed by an explicit computation, and you identify what this tower of states are. And the fact that this is an n equals to 2 supersymmetric compactifications make this analysis possible, okay, where you can actually identify what states becomes light. This confirms the asymptotic behavior suggested by the Swampland distance conjecture, but the real interesting question is what happened at finite but large distances. Since the whole point of this discussion is whether you can go to larger than the Planck scale or not, of course, you cannot go parametrically large, but how large can you go? And this is still a question that would be of interest given the confirmation of the Swampland distance conjecture. And one last point before we stop is that here in that studies, it was also shown that quantum corrections from integrating out these wrapped D3 branes would generate a potential for the field, as the Swampland distance conjecture suggests. And this is very different from the classical effects that I mentioned in this lecture. So previously, when we considered the back reaction of the Saxion field, it generated a potential for the axion. It generated corrections to the metric, the kinetic term for the axion that looks like this. This was a classical effect. But in the papers that I mentioned, this is the effect of integrating our loops of BPS states. And yet, they take the same form. And in general, if you are in a general point in the moduli space, both the classical back reaction effects and the quantum corrections should be included. But we don't know which point of the moduli space we are at, but in general, either one of these contributions could dominate. But regardless of what contributions dominate, we will still have to address similar issues to actually find out what is the dynamical field range by actually solving the equation of motions. Okay. So I think I'm going way over time. Okay. So it is actually a good place to stop before we continue next time.
String theory inspired inflations. Are there any other interesting models apart from these axion-related constructions which are interesting?
So it depends on whether you are particularly looking at models that give gravity waves or not. So there are also models that don't give detectable level of gravitational waves, but give rise to other signatures, like non-Gaussianities. So one example is something called dBi inflation. It's somewhat motivated, but it's also very hard to realize in explicit string models. And the idea is that in string theory, like at least the scalar fields that live on the branes, the kinetic term is not canonical. It takes this very interesting square root form. And you can work out what is the signature of this model. Turns out the gravitational wave signature for this model is suppressed by this interesting feature. So it's actually giving rise to undetectable level of gravitational waves. However, because of these kinetic interactions, it could give rise to interesting shapes of three-point functions of the CMB. So people have been looking for this kind of strange shapes of non-Gaussianity. And shapes here means the momentum dependence. So what is interesting is if we can go to higher point correlation functions of the CMB, you can learn more interesting physics, in particular the dynamics of inflation. If we are only looking at the density, the two-point functions, the thing that we characterize the two-point function is this tilt, which is just one number. But if you were to write down the three-point function, it's the complicated functions of momentum. And the usual models of inflation, slow roll model, give you a shape that peaks in the squeeze limit when one of the momentum goes to zero. So if you can imagine momentum conservation tells you that the momentum vector should lie on the triangle. And the squeeze limits means that one of the momentum goes to zero. So if you were to look at the three-point functions in the K space, the peaks of the function is at this configuration. Whereas models with strange kinetic term has the peak at the equilateral limit when all the momentum are comparable. So it's very different in character, and also the amplitude is much bigger. But at the moment, the constraints on shapes of this type is also getting stronger.